So hi everyone, welcome back to the third week of this series of lectures on the statistical mechanics of disordered systems. So the first thing I would like to do is try to wrap up the main message I would like all of us to remember from all of our work of the last 2 weeks. And for me, the most important thing is that we remember this result that I call the Convex selection principle that we have seen last time. So I wrote it again here on the slide. So let's go through it together one more time. So the statement is that if we have a function which is it should say RD here, which is convex, so it's jointly convex in these two variables, and such that when we set t equals 0, the function we obtain is C1, and also such that each time we touch it from above, touching from above by a smooth function means there exists phi and a point such that f minus phi has a local maximum at this point tx. So whenever this happens, whenever we touch from above with a smooth function, then at the contact point, actually the equation is satisfied by this smooth test function. If all of this happens, then f is a viscosity solution to the equation. Okay. So this is something that I want us to remember, because this is going to be the mechanism by which we're going to solve the class of problems that we're going to discuss this week, namely statistical inference. But just to perhaps completely close the conversation on the Curie-Weiss model first, let me also remind you that using this result, we prove the following statement, that if we denote by Fn the free energy of this generalized Curie-Weiss model, and if we assume that that when we set t equals 0, this function Fn of 0, comma h converges to, let's say, psi of h. So if we assume convergence and moreover that this limit function is C1, then we can apply the result above, and we obtain that Fn converges to a function f, which is solution to the equation displayed. Okay, and separately from that, we know, because of this Hopf formula, that because the initial condition is convex, we can write the solution using this in this variational way, and that recovers the result we initially got using large deviations. And perhaps it's so in fact here I'm already kind of, so there's a question in the chat about whether it's enough to have the statement on the dense set. In some sense, last time I stated a theorem that was talking about a dense set of points, and then a corollary that speaks about touching the function from above. And we prove the corollary by explaining that this set of contact points is dense. Okay, so in some sense, this is already a post-processing of what last time we had called convex selection principle. And we will, yeah, so this will be enough for us. It's like every contact point will do. In some sense, these contact points are extremely nice for us. They are designed to be as nice as possible. So we don't need to further wonder if we can remove a small set. Yeah, thanks for the question. So as usual, feel free to ask questions in the chat. Yeah, and perhaps I thought that it would be worth to spend just 5 more minutes, or maybe a bit more minutes on one point, which is whether or not this assumption that psi is C1 is necessary, because it seems that the proof is kind of trying to leverage on this fact, and it's perhaps not very intuitive that this is a necessary assumption. So I try to insert a little bit of the intuition that something like this could be necessary when we did large deviations, because we saw that, at least as far as large deviations is concerned, there is some similar psi C1 assumption lurking around there. And we argued that it was a necessary assumption. But perhaps it's useful to revisit this example in the current context. Like if I want to contradict the statement that is currently on display by removing the assumption that psi is C1, only assuming that psi is Lipschitz. So I'm going to essentially transcribe the counterexample we saw in this large deviation context in this present, let's say, framework of discussing the Curie-Weiss model. And so we are going to, let's say, counterexample. If psi is only C1, it is only Lipschitz. Sorry. So I'm going to build it the same way. I'm going to, so you remember when we defined the generalized Curie-Weiss model, there are two things to choose. There is the nonlinearity, like this function psi, which is the square function for standard Curie-Weiss, but we can choose other functions. And there is this underlying measure, which we were writing Pn, which in the normal Curie-Weiss is just a product of Bernoulli's, but which I can choose the way I want, provided this convergence of Fn of 0 is satisfied. So here I'm going to choose the measure Pn to be just with probability 1/2, we put all the spins to be ones. So this is the Dirac at the vector of length n, which is made of ones. And with probability 1/2, every spin is -1. Okay, and I'm going to, for this function psi, I'm going to take the minus square function. No, it's this one which I used as a really, let's say, a prominent display of the fact that there could be issues with the approach using viscosity solutions. Okay, so let me, because the measure is so simple, it's only charging 2 points. And on these 2 points, we can compute everything explicitly. On this example, we can explicitly compute what is the free energy. So in this case, Fn of T and H. So remember, in general, it's 1/n log, and then some integral with respect to Pn. But here, Pn is this very simple measure. So it's going to be just 1/2 times the exponential, in which everywhere where there's a sigma, I substitute by a 1. So it's going to be T, and then, so if I compute 1/n sum of sigma I, it just gives me 1. And then I'm supposed to compute psi of that thing. So it's going to give me -1. So I'm just going to get minus nt. And then it's plus h times this sum of sigma I. So I'm going to get plus hn. And now there is the other term which comes from the event when all the spins are -1. So the first part, it's squared, so there'll still be a minus Tn. And then it's going to be minus Hn. Right? Is it clear for everyone that this is the free energy? Okay, so let's think about how this behaves when n goes to infinity. So first of all, there is this minus Tn, which is on both terms, so we can factorize it. Then we take the log, we divide by n. So it will remain in the limit. There will be this minus T. Oops. Okay. And now we have to think about this H part. So let's now ignore, formally you set T equals 0 if you want, like now it's gone out of our computation. So we have exponential of Hn, plus exponential of minus hn. So let's say h is positive, then exponential of hn will be vastly dominant. So we're going to get, so after we take the log and we divide by n, we're going to get just h. Now, if h is negative, the other thing that will happen is the minus h, which will dominate. So overall, it's h when h is positive, it's minus h when h is negative. So overall, it's the absolute value of h which remains. Okay, so that is the limit for energy. And if we were to believe the statement, which I'm trying to contradict here, because observe that when t equals 0, the function is absolute value of h, it is not C1. Okay, and that was the point. I want to try to contradict that the statement I showed before. So I have to find something which is not C1 when I say t equals 0. And if we were to believe the result, we would have to think about the following PDE. So dtf, and then the nonlinearity is minus the square function. So I'm going to write plus dhf squared equals 0. And the initial condition is whatever we get as the limit when we set t equals 0, which we just saw is absolute value of h. Okay. So if I kind of naively believe that the statement we discussed earlier is true, it would have to be that this thing we get in the limit is the solution of this PD. Okay, so I claim this is not the case. And one easy way to see this, perhaps, is that by the comparison principle, the solution to this PDE is non-negative. Okay, because the 0 function is a solution, and initially our solution is non-negative. And alternatively, you can just write the Hopflax formula, and you will see that it's a non-negative function. So in fact, you can compute explicitly what is the solution, and it's done in the handwritten notes. But I don't need to compute it in order to observe that this solution is not h minus t. Okay, we have let's say f of th not equal to absolute value of h minus t. And you see that this function, okay, so observe also. So this is already a counterexample to this consequence I displayed earlier. Okay, and in particular, it contains a counterexample to this main theorem, to the convex selection principle. Okay, so observe that the mapping, I mean, this solution, this absolute of h minus t, is convex, is jointly convex in its arguments. And it solves the equation almost everywhere. Okay, this is if you differentiate, like except when h is 0, if you differentiate in h, the derivative will be plus 1 or minus 1. And if you differentiate in t, it's going to be minus 1. So the equation is satisfied at every point of differentiability. So here is this is a counterexample. And just I mentioned in passing that you can devise another measure Pn that has the same initial condition absolute value of H, but for which the free energy does converge to the solution to this PDE. This is also explained in the handwritten notes. So it means that if you want to, if you get away with, if you're considering a situation when this initial condition is not C1, then the limit free energy will not be a function of the initial condition. There will be situations in which you have the same initial condition, but the rest of the limit free energy is different depending on the model. Anyway, you can see more details about this in the notes, but I thought it was interesting to point it out. All right, so there are questions. Let me see. Yeah, so to me, the interpretation, at least from the point of view of large deviations, is that when you do this dualization or something, it's okay. So when you the question is whether or not the probability to get the magnetization inside some region will be a convex function of the argument. So if I look at least that's the way I think about it. When we did large deviations, we essentially the critical question is whether, okay, let me write it like this, is whether this function is convex with a function of M. So in some sense, when in full generality, when you do this calculation of psi star, what you recover is the convex envelope of this function. And when psi is C1, essentially it tells you that this function is strictly convex. So if I display to you the convex envelope, in fact you know what is this function because there is no other possibility. And when the initial condition is only Lipschitz, this other function will have flat pieces, and so you cannot know what is the underlying function. Okay, so something like this. I'm not sure if I explained it well, but and so but just to illustrate this intuition, the other example I have in mind, which does converge to this viscosity solution, is when you take Pn to be of this form. So let's say, so instead of having these two Diracs at everybody -1 and everybody +1, you can say they're going to be, I'm going to pick a number at random between -1 and 1, and then I'm going to put a delta at this number. Okay, so this is a different initial condition. It's a different measure, sorry, than the other one, but this one will converge to the same. We will have the same initial condition. It will also satisfy that when you set t equals 0, it converges to absolute value of h. But when t is positive, it will converge to the solution to this equation. Okay, so yeah, it's okay. And from the point of view of the PDE, my intuition is that when you try to create singularities, you need to push the second derivative up and down. But if the singularity is already present, then in some sense you only need to keep it alive in order to get a counterexample. Something like this. All right. So yes, and when I say the notes, I mean the handwritten notes. Cool. Yeah. So if there are no further questions, then I'm going to start speaking about this perhaps a more interesting topic in which there is no large deviation lurking around, which allows us to solve the problem easily. And this is going to be these models coming from statistical inference. So I think it's chapter 5. So I'm going to focus on a particular problem, which has the following form. So I assume that there is a big vector. So let's say so n is very large. I have this large vector x bar, and we observe a noisy version of the matrix x bar transpose. Okay, I put a star to denote the transpose. Okay, so more precisely, we observe something like this. Where this is just a matrix full of independent Gaussian standard Gaussian random variables. Yes, so star is the transpose. So explicitly, this means that for every I and j between 1 and n, you observe square root of 2t over n x bar I, x bar j, plus wij. Okay. I don't assume symmetry. It's more convenient, but yeah, basically you could reduce one to the other, but for writing things up, I don't assume that W is symmetry. So we observe this for every pair I and j. And so I'm going to explain more precisely what are the assumptions. But before, I thought it would be nice to give some motivation. And I mean, it's interesting to wonder about the observation of small rank matrices. But it's nice to know that it shows up in a variety of contexts. And perhaps one context is recommendation systems. Another context is community detection. And it's perhaps less obvious that it can show up in community detection. So I thought it would be nice to spend a few minutes explaining in rough terms how it shows up there. Okay, so it will be a bit of an informal discussion, trying to point out a connection with problems of the sort of community detection. And yeah, before I go into this, maybe I should have said the sort of things we want to observe here is we want to say when is it possible to recover information about what we care about the signal x bar, and when is it not possible? And if it's possible, how much of the signal can we recover? And just like with the Curie-Weiss model, we will have phase transitions in our problem. So depending on the value of t, there will be a phase in which we cannot recover anything about the signal. And after a certain threshold, we will start to be able to recover something about the signal. Okay, and maybe we can even say explicitly what is this something, in the same way that we could identify the magnetization in the limit of large N for Curie-Weiss. Okay, so let's say one motivation. Now I'm going to discuss community detection a little bit. So I'm going to take a few minutes to think about a problem of community detection and try to informally draw a connection between this question and the question I just described. Yes, so let's take a model with two communities. So the nodes are individuals, if you want. They are index from 1 to n, and just like in the first lecture in the introduction, I'm going to assume that there are two communities, and let's say they have equal sizes. So no, I'm going to, otherwise, yeah, there will be some, whether or not n is odd or even, okay. Anyway, +1 or -1, let's say there are decided, so each individual I tosses a coin and decides if it's in the community +1 or the community -1, and the coin is so indicated by a vector x bar of IID random variables. So +1 with probability 1/2. And -1 with probability 1/2. Okay, so we have this vector. It tells us whether each index I is in community +1 or in community -1. But we cannot observe this vector directly. So what happens is that these individuals will form connections between each other, and they will prefer to be connected with people of the same group, let's say. So we draw an edge between I and j. And I'm going to set it up like this. So I'm going to say that the probability that we draw an edge between I and j is dp over n if x bar I equals x bar j, and is dq over n if x bar I is different from x bar j, and I'm going to fix p plus q equals 2. And the reason I do this is that in this way, the average degree of a node is approximately d. Okay, so I have these two parameters, three parameters, d, p, and q, and let's say I know these parameters, and then people connect to each other according to these rules, and then I observe the connections, and I ask myself if I can recover the identity of the two groups. Does the question make sense? So we have this random graph. We see these connections, and we try to figure out the labels, if you want. Where is 2d equals n? No, 2d is not equal to n. It's just that approximately each node has n over 2 other nodes in the same group. So you have approximately p connections to people in your group. Sorry, DP connections with people in your group. DP over 2, I'm going to manage. And for the other group, you're going to have DQ over 2 connections. So in total, you have DP over 2 plus DQ over 2, and P plus Q is 2, so you get D. Okay. And so we think that P and Q are a bit different, so it's not, they don't match the same way within group or between different groups. If you want, it's like an Erdős-Rényi graph, but there are 2 communities. And here, yeah, so here I use a fixed D, but I'm going to take the limit of large N and then large D, because I want, you know, the things I talk about are mean field in some sense. So I want that, so at least in some sense, in fact, there are lots of connections. So at some point, I will want to let D go to infinity. Just so you know. So what happens? So for each pair, IJ, we can, you know, we are monitoring if there is a connection between I and J, and this observation is a Bernoulli random variable with a certain. So we observe a connection which is a Bernoulli random variable with parameter dp over n if x bar I equals x bar j, and it's a Bernoulli random variable with parameter dq over n if x bar I is different from x bar j. Okay, so if I want to, yes, so you can think of P as being larger than Q. In fact, what I'm going to discuss would also, yeah, will be kind of symmetric in P and Q. So you could also imagine that they prefer to connect to people in the other group, but it's more natural to assume P is larger than Q, indeed. So let's say P is larger than Q. Yeah, and if P is equal to Q, there's no chance. But what we're going to see is that even if P is only slightly larger than Q, okay, yeah, we cannot do this. Okay, I just want to draw the connection with the first question, but we'll see that when P is equal to Q, there is no signal, indeed. So if I want to summarize this in just one line, instead of writing if, I can write it the following way. So I can write D P plus Q over N plus D P minus Q over N times X bar Xj, X bar I, X bar J. Okay, because when this is 1, I get dp over n, and when the same thing is -1, I get dq over n. Okay, and these are the only 2 possibilities. Okay, so this is the random variable. And now the thing which here I'm just going to wave my hands about the fact that this is plausible. But okay, so I'm just going to observe the mean value of this random variable and its variance. Then I'm going to say, oh, but if this was a Gaussian with the same mean and variance, then the problem would in some sense be similar. And this I'm not justifying. This is a difficult part of the argument. But this is how the connection is built. So the mean of this random variable, well, it's just a Bernoulli, so it's D P plus Q over N is actually P plus Q is actually 2, we said. Oh, and I make a mistake. No, that's fine. So sorry, I just had a little pause. So P plus Q is 2, so it's 2D over N plus D P minus Q over N times X bar I, X bar J. And the variance so the variance is well, is also P. But I'm going to argue that as far as the variance is concerned, I can neglect the lower order part. Okay, so I have to explain what's going on here. So in the mean, this thing is a constant. So if I tell you that I observe a constant, like the only informative part here is this part. You want to know about X bar I, X bar J. So if there is a constant around, it's not really useful for us to learn about X bar. So I'm going to just ignore it when I look at the mean value. And that's why here I don't neglect it, because this is just, like the real random variable I should look at is this Bernoulli minus 2D over N, if you want. Okay, and this is what I should think about. And then the mean is without this constant. Okay. So we ignore. In terms of recovering X bar, this is not going to be useful. And now the variance, on the other hand, is really, there is really this amount of noise in the variance. And yes, yeah, okay. So we're going to see in a second that the other term is of lower order. So I'm not writing it in the variance. Okay, so this is I wave my hands some more, but let's just assume this is indeed negligible. And the point that I want to make here is that this problem is equivalent to the situation in which I would have the same sort of observations, but where the random variables are Gaussian. So similar to observing D P minus Q over N X bar I, X bar J, plus this amount of noise, so square root of 2D over N times, I just put a standard Gaussian, Wij. Okay, and this similar to observing, this is what I don't justify, but this is, if you want to make it rigorous, it's not straightforward. And it's the sense of this is in the limit when N goes to infinity, and then D goes to infinity. Oh yeah, okay. I lost a factor of 2 somewhere. Sorry. So here there was a 2. I'm sorry. Yeah, that's just when we do dp plus q plus d, so that it matches the formula above, there's a 2, which I lost. Sorry about this. So then I have to remove some 2s. All right. Yeah, sorry, that's but now you see that, okay, this is of the form yeah, no, T is multiplying so this is of the form of the problem initially posed. So initially it was square root of 2t over n, x bar I, x bar j, plus w. And I want the current problem we're discussing to stabilize around this. So what I would like to do is renormalize this. I could just divide everything by square root of d over n, so that it's so that it looks like the original problem I discussed. Okay, there is no factor in front of the w. And in this case, I see that what I would like to keep fixed is so I would like that square root of d times p minus q remains of order 1. Okay, and so this is this also reveals the right scaling. So you see that the scaling I use is with p minus q of the order of 1 over square root of d. And that's why there was something I neglected earlier, and it's because p minus q is we take d large and p minus q becomes small. Okay, so lots of things have been going on, but I wanted to explain this because I think it's interesting to have in mind this this problem source, let's say, because part of what has been driving our recent activity is to consider marginal versions of this question of trying to understand what we can recover from x bar, observing x bar transpose plus some noise. Okay, so I hope I gave some sort of sense of why community detection can perhaps be related to observing a rank 1 matrix plus some amount of noise, because in some sense, up to approximations in some place, this is what shows up. It's also related to a question that someone asked very early on. I think, when I introduced spin glasses at the beginning, the noise is Gaussian, and someone asked, what about if the noise is not Gaussian? And I said, but you can verify in advance in some sense that as long as the noise has the same first and second moments, the limit free energies will be the same. And I have not explained why this is true, but here I'm using the same sort of argument that if we match the first and second moments, then things will be fine. And yeah, it's a nice way for me to point out that you can imagine more complex models than this. So for instance, t, I mean, the t is just some other parameter. So there's a question in the t about the t, in the chat about the t. It's just there will be some correspondence between the parameters in the community detection problem with some t for some well-chosen t. That's all I mean. It's just you can do a matching. It will depend on what the square root of d times p minus q converges to when you send it to infinity. Yeah, and you can imagine more complex models because it's possible that the community structure is more involved than just having two communities. Maybe there are more communities and they like or dislike each other in some complex ways. So maybe more communities. And the way they will want to pair to one another is will be dependent on some belongings to different communities. So there's a question about why do I have square root of d over n here? This is because I want to match that the variance is d over n. Okay, so I put this square root of d over n. Yeah, I'm sorry that I was a bit quick. I thought Yeah, so it was simpler to explain than I'm realizing it is now, but okay. And so in general, instead of observing just this x bar transpose guys, you could imagine more complex situations. So, oops, this could be encoded by a matrix, say big X in R. I'm going to do n times k. So let's say capital K is fixed and is going to encode the number of different groups. And and we can still assume that so each individual is going to be represented by a row in this matrix. And in this row, there will be k coordinates, and maybe it will tell us, this individual number I belongs to community 1, does not belong to community 2, does belong to community 3, etc. And so we can record the belongings by just using a vector of xk for each individual. And then the way the connections will be drawn will be according to some computation that involves the belongings of individual I and all the belongings of individual j. And so in this case, we are going to observe a noisy version of the second order tensor product of x bar multiplied by some matrix. Okay, so where which I think of as a matrix in n squared times k squared. If this is a bit of, and A is a fixed matrix. So I'm going a bit fast here. I don't want to explain in details what this tensor product is, or I would just like that you have some sense of which class of models this specific model I'm going to focus on belongs to. So I'm going to, during the whole week, I'm always going to focus on the first thing I said, we have one vector and we look at x bar transpose plus noise. But I just would like that, I would just like at the beginning of discussing this to give some sort of sense of the class of models that in which this belongs. Okay, and this is perhaps the largest class if we stick to order 2. And then, once you have decided that this makes sense, you could also consider a higher tensors. Instead of order 2, you could say, why not order 3 or order 4? So, or even more generally, we could think of trying to understand models of this sort. So we observe a noisy version of this guy. Okay, and so I say all this because so this is the most general model I'm ever going to mention. And last year I talked about related problems, and I also focused on in this OOPS summer school. And maybe some of you have seen some of these videos. And I also focused on this simple model X bar transpose. But there I use a method which works nicely for X bar transpose, but will not apply to these more general models. Or at least only to some of them, not to all of them. And a lot of my recent activity was focused on trying to find a method that will actually cover these more general models. And as you know, part of my motivation is that I still think that all of these models, even though they look a little bit complicated, they are still kind of simpler versions of what happens in spin glasses. And since I struggle with spin glasses, I thought I should try to first make sure that I understand these models, even the most hairy ones with p-order tensor. And and so finally, so the methods we're going to discuss this week, we're only going to discuss it on the simple model, X bar transpose, but it would apply essentially unchanged also to the more general models. And this is, I have to tell you this because otherwise you could just think, why not just use this other method I explained last year? And the reason is that it's not going to extend to all of these models. All right, so if this was confusing, don't worry. This is the end of the conversation about the more general models. After the break, I'm going to define precisely this X bar transpose model, and we're going to study it carefully and with much more details than I did right now. Okay, so this was just to give you a sense of, let's say, the landscape of possible models. But if this was confusing, don't worry, we're going to, let's say, restart from scratch after the break. So let's take a 10-minute break, and I'm happy to take questions if there are. So I already saw a question I had missed. So the question is about PCA. So okay, so let me rewrite this thing I do want to focus on. So perhaps one question you can ask is, I'm going to end up answering the question, but I'm going to make a little detour, which I think is interesting. One question you can ask is, why is there 1 over square root of n? Like, why is this the correct scaling? And perhaps you can make some arguments about trying to count the number of observations, the signal-to-noise ratio, and doing some heuristics that suggest this is the right scaling. But this would be a very heuristic argument, and it's context. So we observe, I'm just going to restate it. I'm going to call it y square root of 2t over n x bar transpose plus w. So where x bar 1, x bar n is the vector of IID bounded random variables. And below, I'm going to write Pn as before. W is our matrix of standard Gaussians. I should say independent somewhere. So they are independent of x bar as well. And this parameter t encodes the signal to noise ratio. Make sense? And here I'm going to focus on trying to understand the theoretical limits to recovering x bar. So instead of, I'm not going to focus on explicit methods like this principal component analysis approach that we discussed during the break. I'm just going to try to, I'm going to try to answer a different question, which is, what is the best possible thing that one can possibly hope to achieve? So our goal is to understand the let's say information theoretic limits to the possibility of recovering information about x bar. Okay, so in this talk, there will be no consideration of algorithms. There is a problem set in which we compare these theoretical limits with precisely actually this principal component analysis approach. So it's interesting that we can discuss whether or not principal component analysis reaches the optimal best possible thing we can do or not. But yeah, this will not feature in the lectures per se. And yeah, I just want to a little reminder. So I'm going to try to imagine that we take the best okay, let me state the reminder first, and then so let's say if I have a function in some L2 space of the probability space, and f is some sub-sigma algebra. Then when I look at the infimum over all functions g which are f measurable, so f is not the complete sigma algebra. It may be a smaller sigma algebra than the underlying sigma algebra of f. If I try to find the best f measurable approximation of a function, in this L2 sense, then this will be the conditional expectation of f given a script f. Okay, is achieved for G equals the conditional expectation. Okay, I encourage you to verify this. It's a simple exercise using the definition of conditional expectation. You can even think of it in geometric terms. You're doing an orthogonal projection, and there are some orthogonality properties involving the conditional expectation. So in our context, we want to recover information about X bar. And what we observe is this observation Y. So in some sense, what we want is to find the best Y measurable function that approximates X bar. Okay, so we are ready to consider any function of the observations. So it's any function of the observations is any Y measurable function. And we're trying to find the best approximation of X bar. So in our context, we would like to find, well, we're interested in computing the infimum over, let's say, Z, which is Y measurable, of expectation of X bar minus Z squared. And so this will be achieved by, again, the conditional expectation. Okay, so X bar minus the conditional expectation of X bar given Y. Okay, so it's if you want, it's from a theory point of view, and in this L2 sense, the best possible guess you can make on X bar, given the observation Y, is the conditional expectation of X bar given Y. Okay, and I want to understand how good this function is. How close expectation of X bar given Y is to actually X bar. This is what I want to understand. Okay, so maybe we can call this this is often called the minimal mean square error. Minimal mean square error. And so maybe we're going to denote this MMSC n, and this will also depend on T. Okay, and perhaps what I would like to understand is the asymptotic behavior of this quantity. And maybe if you, like, perhaps it's also a valid point to observe that what we're really observing is a noisy version of X bar transpose. So perhaps it would be best to ask about recovering X bar transpose instead of asking about recovering X bar. So maybe also consider the expectation of X bar transpose minus this same conditional expectation, X bar transpose given Y. Okay, and this also could be legitimately called a minimal mean square error. And here I should say, so this guy is a matrix, so maybe I should say what these absolute values mean in this context. So with the notation, It's just that you sum the square of the coordinates of the matrix. So it's so let's say whenever A and B are two matrices of the same size, we're going to write A scalar B to be just the scalar product component by component, like, as if they were just vectors. Say for the entry-wise product. And then this thing is A scalar. Yeah, and I think it's useful to observe that this may be a better quantity because if you imagine that the law of X bar is invariant under a change of sign, then there's no way you can know if you can make the distinction between seeing X bar and seeing minus X bar because you're seeing this X bar transpose, right? So they are multiplied. So if I secretly replace X bar by minus X bar, you cannot know by observing X bar transpose. And if the law of X bar has this symmetry by multiplying by a -1, then this expectation of X bar given Y will be 0 as a consequence, okay? Because the observation is unchanged by the change of sign. And so just by symmetry in this case, this guy will always be 0. So there are ways to address this that we can just decide in some technical way to break the symmetry, and in this case the quantity become meaningful again. But yeah, perhaps a cleaner way out of this inconvenience is to actually focus on this quantity instead. Okay, so this is the minimum mean square error, and I would like to understand what is its value. Is it are there T's such that this is that there is just no information gain, like this thing is actually of the same order of magnitude as if I had computed expectation of absolute value of X bar squared? Are there parameters for which this is extremely small? This is what I want to understand. And this motivates the study of the conditional law of X bar given Y. Okay, so I want to understand more precisely what that is. And so we're going to, so let's try to write down the conditional law of X bar given Y. Okay, so this is I'm going to do an informal computation. Where there will be 0 divided by 0 appearing, but okay. So I'm going to do an informal computation to figure out the conditional law of X bar given Y. So let me write it like this. Yeah, I'm going to try to compute this and pretending that let's imagine that we discretize a little bit all of the variables so that all of this makes sense. And so by Bayes' rule, this should be like this. And then, okay, so in the numerator, the probability that x bar is equal to x, by definition, is given by this measure dpn, right? So it's dpn of x. And then if I have sampled x already, and I ask, what is the probability that to observe a particular realization of y? Then it's just about aligning the noise W so that I observe y. Okay, so the other term will be, and W is full of Gaussians. Okay, so minus, it's going to be minus 1/2 of y minus square root of 2t over n x transpose squared. Maybe I should write dy or something. Okay, so this is because let me write this in another color. This exponential thing is informally the probability that W is equal to y minus square root of 2t over n x transpose. Okay, this is what I'm writing. This event here is the same as the event that y is equal to little y, if you're already given that x bar is little x. Okay. So it's an informal computation. And then I have to divide by the probability that capital Y is equal to little y. And this should be the sum over, so on top is the probability that y is equal to little y and x bar is equal to little x. So if I sum over all possible x, I get the denominator. So I'm going to just sum over little x. I'm going to use a different notation, x prime, let's say. And now I have dy's on both slots, so I'm going to just erase them. Okay, and this is not a rigorous computation. But yeah, in my experience, when I try to explain it rigorously, people find it more confusing than when I try to do it like this. But here is a rigorous statement that should convey the same information. So define so I'm going to do one more simplification, which is in the exponential, I could expand the square. And I have this exponential of minus y squared in the numerator and in the denominator. So I'm going to just erase it. So I'm going to define just what remains in the exponential, which is square root of 2t over n y dot x transpose minus t over n x transpose squared. And the claim is that if I compute the conditional expectation of x bar given y, then this is going to be written as, like, so now I'm yes. There's a question in the chat about this y minus square root of 2t over n x transpose is a matrix, and then we take this norm, which is the norm squared is the sum of the squares of the coordinates. So it matches with what this matrix of independent Gaussians is doing. Okay. Yeah, I'm simplifying. So I don't put the y square because it's both in the numerator and in the denominator. So I could have kept it, but I prefer to simplify it. Okay, so I'm going to erase it. Does that make sense? I cannot simplify the other terms because in the numerator it's written x, and in the denominator it's written x prime. So each time, you know, these other terms will not simplify, but the y is simplifying. Okay, so I integrate this measure and I get so f of x exponential of hn0 tx dpn x divided by I mean, I could write x prime if I want, but I'm going to x prime. I could as well delete the prime, right? Because it's just an integration variable now. So let me delete it. Okay, cannot delete it without destroying the display. Yeah, there's a little 0 on top of h because very soon there will be an h, and I want the h to be, the h will stay with us for much longer than the h0. So I just have some notation for h0. So it's just some, you know, maybe I could have called it h tilde or h hat. It's just some preliminary version of the true h, let's say. Does that make sense? So I did not justify it properly, but this is the like the last line is a valid statement and it's a true statement. Okay. The displays below are not rigorous statements. So it's possible to make sense of that display rigorously, right? It's just that in my experience, if I try to explain it rigorously, people find it more confusing than if I do this. So I do it. And well, here it comes. This looks like a Gibbs measure. Okay, so we are going to, you know, we are in a setting which resembles the one we have been dealing with Curie-Weiss. So one difference with Curie-Weiss is that now this energy function hn0 of tx is random. Okay, so if you wish, there are two levels of randomness. First, we pick x bar and the noise w, which defines for us this capital Y guy. And from this realization of the noise, we can define, like for each realization of the noise, we can define the measure that is displayed here. Okay, and so here is the notation we're going to use. So just like for Curie-Weiss, I want to use this bracket notation. And it will be useful for us to remember sometimes that this is also the conditional expectation. Okay, and I do, sometimes I do like to write it in integral form so we can also think of it like this. So if we decide that this P x bar slash y is the conditional law of x bar given y, so it's a random measure, then this is what the notation means. And okay, so the advantage of this notation is that now I want to think of x as being a random variable that is sampled according to the law of x bar given y. Okay, so if you want, I define a new probability space with this expectation with the angular brackets. And in this new probability space, the random variable x is sampled according to the law of x bar given y. Okay. So I think it's a good time for me to stop. Thanks for your attention. I'm happy to take questions if you have any. So there's a question in the chat about higher order Bernoulli models. Maybe, I don't know if you want to clarify I can try to answer. I'm not sure if I completely understand the question. So when you have several communities, it's true that it will be, when you start to encode your problem in, when each individual is represented by a vector instead of just a scalar, then at the level of the set of parameters, you will have to use some higher dimensional version of this H that we were using for query-wise. And so indeed, so there will be some Hamilton-Jacobi equation as before, but this Hamilton-Jacobi equation will be higher dimensional. And indeed, there will be threshold regions which are I know, like hypersurfaces in dimension D or something. But okay, please tell me if this did not answer your question. Yeah, and maybe hypergraphs is related to the tensor version when you take p equals 3, for instance. So that the edges are like triangles, and you're deciding that. But in terms of the structure of the partial differential equation, the dimensionality will be only related to the length of the vector with which you encode each individual. And part of the thing that is nice with this way of approaching the problem, let's say, is that the initial condition is only a function of how you define these x bar guys, and the propagation of the equation is when you start to wonder if it's a hypergraph or what is the structure of the community or what they are doing.